Modern vehicles operate as complex software-defined networks, functioning as giant, vulnerable computers on wheels. When that software fails, the results aren't limited to a frozen screen. A digital error in a 2-ton machine translates directly to a physical, often fatal consequence. To protect passengers from random hardware glitches or electrical interference, the industry relies on a standard called functional safety. The core requirement of safety is to fail safe. If a sensor fails, the system is designed to unlock the doors, cut power to the motor, and hand control back to the human driver. But because modern cars are wirelessly connected to the outside world, they also require a second guardian, cybersecurity. Security operates on a different requirement, fail secure. If an intrusion is detected, the system locks the doors, blocks incoming data, and seals off the vehicle to prevent a hijack. These two mandates, one built to open up, the other to lock down, create a structural conflict within the vehicle's architecture. Imagine a Level 3 autonomous vehicle traveling at 120 kilometers per hour. Suddenly, the braking controller is flooded with corrupted data. The safety logic diagnoses a communication failure and orders the car to cut cower and pull over to the shoulder. Simultaneously, the security logic identifies a potential cyber attack and orders the brakes to ignore all incoming commands to prevent a remote hijack. Because the two systems cannot communicate or compromise, the braking controller freezes in a total deadlock and the car crashes. When safety and security systems are isolated, the protocols designed to protect the passenger can inadvertently cause their death. Engineers stacked protocols, placing the safety layer below the security layer. When a hacker injects a malicious packet, it hits safety first. Safety assumes a physical glitch and trashes it. This creates error shadowing. The security layer never sees the attack. Hackers can probe millions of vehicles without ever being detected because the safety layer is quietly discarding the evidence of the attack. Sophisticated attackers realize they don't need to break heavy encryption. They only need to trigger the safety system's own defense mechanisms. By flooding the network with noisy, garbage data, a remote hacker can intentionally slow down critical driving tasks. The vehicle's watchdog monitor sees this lag, assumes the processor is failing, and triggers an emergency reboot. The safety system may then permanently cut off communication to the glitching sensor, effectively blinding all of the car's autonomous features. The attacker achieves a total system shutdown without writing a single line of malicious steering code, simply by tricking the car into disabling itself. Engineers eventually discovered a hidden synergy. The mathematical logic used for safety monitoring and the cryptographic checks used for security are built on nearly identical principles. Safety uses alive counters to check for physical glitches, while security uses freshness values to block hackers from replaying old messages. Modern architecture merges these into a single protocol layer. They are no longer separate operations. They are one unified check. When an error occurs, this unified layer can mathematically prove whether the fault was a frayed wire or an active cyber attack. This provides the vehicle with a unified diagnostic path, clearly distinguishing between hardware failures and malicious interference. Returning to our 120 km/h highway crisis with this unified architecture, the outcome changes. When data floods the brakes, there is no deadlock. A dynamic arbitrator takes charge of the situation. The system enters a state called fail operational, seamlessly shifting steering control to an isolated, unhackable backup computer. The backup computer locks out the external hackers while safely guiding the vehicle to the shoulder of the highway. Physical safety and digital security have become inseparable disciplines. For a software-defined vehicle, a system that is not secure can never truly be safe.